Hello everybody and welcome back to Calc 3 Online. So today I just want to do a little bit of review problems from chapter 13 with our vector valued functions. And it's just like a whole bunch of random problems that I think are good, kind of on the harder side of things, which I think is good to see some of these. So this one, you have this vector valued function right here. And they want you to show that the angle between the unit tangent vector of it and the z-axis is the same, like always. And so you basically have to show that like that angle is like constant. So let's find the unit tangent vector. So that's the vector like capital T, where it's r prime over the magnitude of r prime. So we're going to need r prime, which basically you'd have to do a like a product rule here. So you have like e of t times cosine t. So you'd have to do a product rule there and a product rule also here. If you do the product rule out, you're going to get e of t times cos t minus sine t. And then product rule in the second one is going to be e of t cos t plus sine t. And then derivative of e to the t is just e to the t. So then you need a magnitude of r prime. So magnitude of r prime is going to be e, when you square e to the t, right, you're going to get e to the 2t. I'm just going to write this, I think, for a second right now. So all of that squared plus e to the 2t times cos t plus sine t squared plus e to the 2t. Okay. So this looks kind of messy, but actually it's going to be, in the end, kind of nice. So you can take an e to the 2t out of everything. And then I think I'm going to do this part just in blue. So we have big brackets, I'm going to say here. So we got a cosine squared t, and then we'll have minus 2 cos t sine t. Then we got plus sine squared. So that's the part in blue. And maybe I'll do yellow for this one. So then I have, I'm going to have cosine squared plus 2 sine t cos t plus sine squared. And then I took an e to the t out, which really left me a 1. So like from this term, you're going to have like a plus 1. So all of that is just that multiplication out, basically. And then we have e to the 2t, but this is where things are going to get nice. So let's see if I can pick a different color here. So we have cosine squared plus sine squared. So that is a 1. Then we have cosine squared plus sine squared. That's another 1. This and this are the same, so they're going to cancel out. So really you just have that 1 also needs to be tagged along. So then you have square root of 3e to the 2t is the magnitude of r prime, which I guess you could also write root 3e to just the t. You could like take the square root of e to the 2t. So that means then that was just the magnitude part. So t equals, I'm actually going to just save myself a little work here. So I have r prime, and it has e to the t and everything, but I'm going to divide by this. So it's going to cancel all those e to the t's. So basically, I'm going to get 1 over root 3, just that part right there. And then all these e to the t's are canceling. So we get 1 over root 3, and then we still have everything else, I guess, here. Cos t minus sine t, cos t plus sine t, and then we'll have a 1. Right? So now you need to think about what represents the z-axis. So this is kind of like my hint here. So the best way to you just need something that's parallel. So I would just take k hat. So just take k hat, the 0, 0, 1 vector. And so what we really want to show is if we take the cosine of theta, like basically we want theta to be the same for t dot k hat. I guess t is also a unit vector. Magnitude of t hat, magnitude k hat. And since the magnitudes on the bottom are just their unit vectors, really this just simplifies to t hat dotted with k hat. And if you do this, it's actually not so bad because the 0 here would be dotted with cos t over root 3, which is 0. 0 multiplied here would cancel that term. So, oops, I was pointing the wrong one. This one and this 0. So the only thing that's left over is 1 times 1 over root 3. So you basically get that dot product just simplified to 1 over root 3. And so this implies, actually theta is pi over 6. But not that I think it asked for that specific angle, but it is, you have shown that at every point on the curve, the angle between the unit tangent vector and the z-axis is the same. It's just always pi over 6. Yeah. So another just like important idea is to know that these vector valued functions don't go on forever and ever and ever. I think that I've showed you a lot where they are well defined forever, but you can absolutely have vector valued functions like this where if you want to find the domain and like where this thing is going to be shown in space, you have to literally just do like the domain of like parts like 1, 2, and 3 in a sense. So for part 1, cosecant is just 1 over sine, and sine is undefined basically for every multiple of pi. So we don't want, I guess we can write it like this. We don't want all those multiples of pi, which the fancy way to do that, right, is to just say it doesn't equal like n pi for n, an element of the integers. And then the square root function, so for, we'll code this, okay. For the square root function, you would, you just want the inside of the square root to be greater than or equal to 0, which would imply that just t needs to be greater than or equal to 3. But I don't want to divide by 0. 1 divided by 0 is a weird thing, right? So we don't want to let it equal 3 either. So right now we've got just t greater than 3, and we've got that t can't be a multiple of pi. And then for the last part, we just know that the logs are defined greater than 0, whatever the inside is. So that means that t just needs to be bigger than 2. And so basically this part actually doesn't even matter because we already had to be bigger than 3. So if you're bigger than 2, if you're bigger than 3, then you're already bigger than 2. So this kind of trumps this thing. And really you could just write the answer like that. You could just say t needs to be bigger than 3, but t can't be a multiple of pi. That would be like a perfectly fine way to say the domain. But yeah, if you like graph it, this thing is like a piecewise defined vector valued function. It's going to be only showing up for bigger than 3 t values, but then it skips an infinite amount of multiples of pi. Like it'll skip pi, right? Because pi is bigger than that. And then every multiple of pi after that. All right, this problem is kind of weird, and I like to draw a picture for this one. So it says, find the point on the curve for t between 0 and pi where the tangent line is parallel to the plane. Okay, so what I would do first is I would just draw this picture like I said. So imagine that's my plane, all right? And I want to find the point on the curve. So let's just say the curve is blue. So I don't know, the curve's like, we're going to say that's the curve. So I want to find the point on the curve between 0 and pi where the tangent line is parallel to the plane. So this tangent line, like that, I'm going to say, is parallel to the plane. So that would mean that the normal vector that comes out of the plane is perpendicular to the red tangent line there. So the idea is basically get the derivative vector and set it equal to dot it with the normal vector, and then set that equal to 0, and we can solve that to see when that happens. And that would be how we would find the point when this happens. So we'll basically do that to find like this point where this weird thing is going to happen. Okay, so we got to find the derivative. So r prime is just going to be, let's see, negative 2 sine t, 2 cos t, e to the t. All right, and then I need the normal vector, which is root 3, 1, 0, right? I'm just pulling that out of here. I need that thing to dot with negative 2 sine t, 2 cos t, e to the t, and I need it to be the 0. Nope, not 0 vector. That's not how dot products work. Don't listen to me. It needs to be equal to 0. So let's see, we got negative 2 root 3. I'm just doing my dot product, sine t plus 2 cos t plus 0 needs to equal 0. You got a 2 in both those, so you can take a 2 out. Then, let's see, I'll probably, this is negative still, sorry. I'm going to add the negative 1 over, so I'm going to get cos t equals root 3 sine t. Then divide by sine t, because why not use cotangent? And so this would mean I need cotangent of t to equal root 3, right? And that's a nice one. That's when t is pi over 6. And so if t is pi over 6, now you can just go up to the, position function, because it did say find the point. And we are between 0 and pi, so we're still good. Okay, I just want to make sure my point was between there, which it is. So r of pi over 6, if you plug it in, you're going to get, let's see, cosine is root 3 over 2 for pi over 6 plugged in. So then root 3 over 2 times 2, you're going to cancel the 2's. You're going to get root 3. Then if you plug in pi over 6 for sine, you get 1 over 2. So then 2 times 1 over 2 is 1. Then e to the pi over 6 is a beautiful number that I'm just going to write as e to the pi over 6. And yeah, that would do it. This, that's the position. Like, really, this is the point, I guess. That, blue point right here. That's where it happens. This is another problem that you could plug this into Math 3D. You could plug this into Math 3D, and you could plug r prime in, evaluated, I guess, at the point to see, like, the tangent vector. And then you could really see that all of that matches up with what we just discovered here. But yeah, that would be when this picture happens, basically. All right, another just important part of this unit is just finding integrals of vector-valued functions. And I really do this, honestly, almost because I do this kind of problem just because it's good review of integrals. So there's 3 kinds of integrals here. There's going to be a parts part there. This is a U sub problem. This part, just should label these parts, U sub, and then this is just a, I'm going to call it table. Okay, that's a horribly written table. Let's do that again. Table. Okay. So this is just good practice. So for the parts problem, you want to pick, if you're doing an integral of this part right here, it's parts because really I'm looking, I guess, to see if the derivative of either function in here shows up somewhere, and like the derivative of t is not, I mean, it's 1, so it's kind of, I guess, in there, but trivially in there, and the derivative of e to the 2t is definitely not in there. So it's one of those, though, that if you do parts, you can kill off the t, the polynomial part, with the derivative, and so that's what's really going to dictate my u. So I'm going to let u be t, then du is dt, then dv is everything else, so e to the 2t dt, and then integrals of e to like constant times t, you can just divide by that constant. Yeah. So then parts is uv, so t e to the 2t over 2, uv minus the integral of v du. So I'm going to pull the half out too. So the integral of e to the 2t dt. So, this is my v du. And then that's nice because I got all this stuff. So e to the integral of e to the 2t we just did above. So you'll get a quarter because you divide by 2, e to the 2t. And then we'll basically have to add like the first component of the constant vector. So the second thing is a u sub, because so if you let u equal 1 minus t, then du is negative 1 dt. So I'm just going to say negative dt. We also have that this t I can solve for in terms of u. So note that also t, if you just add the t, add this t over, and then minus u, right? You would have that t equals 1 minus u. So basically I have an integral of 1 minus u over u, du, and then I need to make it negative because of this part right here. So I'm going to actually make that negative and that positive, and that does it. And that is a nice integral because you have negative 1 over u, then plus 1 du. And so you'll get negative natural log absolute value u plus u. And then I just want to go and plug in u equals 1 minus t, like just sub that back in. So then you get negative natural log absolute value 1 minus t plus 1 minus t. And then again, you'll have like a C2 this time. So that is my J component. And then the other one is really quick because it's just one that I want you to know. The integral of 1 over the square root 1 minus t squared dt is inverse sine. So that's just inverse sine t. Again, plus like some C3. And so I kind of ran out of room here, but how about I cheat and I write on the side, because that won't make your brain hurt. So we have t e to the 2t over 2 minus 1 quarter e to the 2t. And then we're going to have comma 1 minus t minus natural log 1 plus t, and then comma sine inverse of t, all of that, plus a constant vector. So I'm going to let you tilt your head and try to read that, but it is just this part, right, then comma this part, then comma that part. Yeah, so that's just like another good review of some different integral techniques. So we do a ton of integrals second semester, so you're going to see a lot more of this by the end of the year. All right, so this problem is, it's actually out of the book, but it reminds me of this like celestial mechanics class that I think I told you in a previous video I took. So we did a lot of these things where we would be given these kind of like word problems where you have some sort of like position, vector valued function, and you have these coordinates of this space station, which are at 649, and the captain wants the ship to coast into the space station. So basically, they're going to shut the engines off, and this thing is just going to end up moving right into here. So the question is, when should they shut it off? And the idea, basically this becomes like the thing that you want to set equal to 649. So I think a picture here is helpful. So the idea, basically it's like you got your spaceship that's moving around like R of t, and there's like a space station here at the point 649, that's my yellow dot. Then you have, when you shut off the engines, you're going to move in a line because you're in space, and that's how things work in space. And the idea is like there's this velocity vector in red here, and you're going to move like along that, and you want to end up like right here. So the question is basically, what sort of point here do you let turn off the engines? And this S is acting, like typically, this is like a vector function for a line is really what this is. And it's this line right here. Typically I'd put a T there, but we're using T here. So it's kind of like parametric inside of parametric. So this S is just acting as like a scalar to say like you shut off the engines, and then you're no longer on your path through R of T here. And you just kind of move in line, and you'll end up like over there at some point. So we need the velocity vector, so we got to take the derivative of R of t. So V of t is going to be 1, and then we're going to get derivative of 2 is 0, derivative of natural log is just 1 over t. Then the 7 is going to go away. For the derivative of this part, I think of this as t squared plus 1 raised to the negative 1. So then when you do the derivative, it drops to negative 2, and then you like multiply by the 2t inside, like the chain rule. And so what you would get is 8t on top, and then t squared plus 1 to now power of 2 on the bottom, because it's like it lowered to negative 2 is how I think about it. So that's my velocity vector. Then I basically make an equation where I plug all this stuff in. So this big messy thing, I'm going to call it star. That equation is going to equal so we got the I component of R, which is 3 plus t, then, so that's R of t, plus S times this, so then we would get really just plus S. Then we have like 2 plus natural log of t plus S over t. So again, S is just multiplied in here because of that. Then we would have 7 minus 4 over t squared plus 1 plus 8t over t squared plus 1 squared. Okay. And all of that, think actually I need to give myself a little more room. All of that needs to equal 6, 4, 9. Okay. So now I basically have a system of equations I can solve. So I can take this and this, set them equal. 3 plus t plus s equals 6. So that would mean like s is 3 minus t. Then I could go and plug in, like do substitution here and here, right? So I know 2 plus natural log of t plus, I'm going to do my substitution. I'm going to stick that in here. 3 minus t is s over t, and all of that has to equal 4, right? So let's see, I'm going to move the 2 over, so natural log of t plus 3 minus t over t equals 2. I'm going to multiply by t natural log of t plus 3 minus t equals 2t. So then you could add t over, so t natural log of t, I'm going to move the 3 over 2 equals 3t minus 3. And I don't know if this is the best way. I'm going to move that back over. Then I'm going to factor out a t. All right, and then, so this kind of thing, these equations are kind of annoying. You could just plug this into a calculator, this equation, and plug in y equals -3 and just see where the two of them line up. It is actually pretty nice though, because you can see that the way I'm looking at it, this, if you could get rid of this, so if you plug in 1, natural log of 1 is 0, then you would get -3. Then this 1 times -3 is truly -3. So like I can kind of just see that that would be 1, t equals 1. But you might need to, like the way you could solve this is graphically. You could just like plug that into a calculator and plug that into a calculator and see if they line up at t equals 1. When should the engines be turned off? Well, basically at time 1, at t equals 1, which you could, if you needed the point, you could go and now plug the point in here, and you could actually get like a actual XYZ spot. If you like this kind of stuff, this is like I took this celestial mechanics class, and you'll do a lot of stuff like this in like an aerospace program. A lot of Calc 3 becomes physics, and this problem is basically just physics is really what this is. But yeah. So there's one more problem that's pretty quick that I just wanted to show. So you have, there's a problem in the book where they tell you, if you have this, what does that look like what's basically happening? And I don't have super long to describe the problem, so I'm going to try to do this, but I'm going to get cut off at 30 minutes, so we'll see how this goes. But I know that these two things have to happen because of the cross product here. And I know that if a derivative vector is perpendicular to a constant vector, then it's like there's some, constant vector, and there's like this plane that defines that constant vector. And I have the derivative vector is always perpendicular to it. Then this is like something we talked about before, where if a derivative vector and its original vector are, if you dot them and it's equal to 0, then that's like this tangent problem that we did, where we actually did it with a sphere, but it works the same with the circle. So basically it's like there's a plane, and then there's like a circle in the plane. And so what this means is that you have a function that's moving around a plane that cuts through the origin. is what this thing would mean. And that's kind of quick because I'm running out of time, but that is what that would mean.